The next type of graph that we want to explore are the graphs of rational functions. So a rational function is a ratio of two polynomials of this form. So px is the numerator and qx is the denominator, noting that px and qx are polynomials. So these are the three forms of rational graphs that we are going to further look at and sketch and understand its characteristic. One of the key characteristics of a rational graph is the denominator definitely cannot equals to 0. So in the function of fx, x cannot equals to a 2 because that would make denominator 0 and the function undefined. For gx, similarly, its denominator has two factors and x cannot equals to 1, neither can it equals to negative 3 over 2, else the denominator will be 0. Something else we have to note is that the degree of the polynomial of qx, if it is greater than the degree of the polynomial of px, we call this a proper rational function. So that would mean simply the denominator has a power x to the power 1, whereas the numerator has a power that is lower, which is x to the power of 0. So these two examples here are examples of proper rational function. What if now the degree of the polynomial of qx is equal or less than the degree of the polynomial px, which also means that in this case the numerator has x to the power of 1, so does the denominator. So this is actually called an improper rational function. So if you look at the next example over here, if this has a power 2, a degree 2, and the denominator has a degree 1, so the numerator has a higher degree, which also means that this polynomial, this rational function is now called an improper rational function. So we can use long division to evaluate all this and make it into a proper rational function. So what we do is later on we are going to have to rewrite our forms as such, and we'll explore the numerical examples very soon. Continuing with key characteristics of rational functions, every rational function has asymptotes, 2, sometimes more than 2. So the dotted lines that you see on the screen are actually asymptotes. They are asymptotes, they are not the x and y axis. So what rational functions often look like, it can come in this form, and if you observed all of this that we are sketching out for you to see, you realize that they tend towards the asymptotes. So there's a tendency for each and every of this graph to tend towards the asymptote, very close to it, but never quite touches it. And also it appears diagonally across each other. So if we are able to obtain the asymptote, regardless how it is like, and we are able to see a point or find a point, we will then be able to know the shape of a rational function. So for example, if I have two random asymptotes such as this, and I can find a point, I will naturally know that this is how the rational function is going to look like. So let me recap. Very importantly, find the asymptote and one point. We are now going to run through the steps to sketching a rational function. This is to help us understand the behavior of rational graphs. At the end of the day, it's a lot easier to use a graphing tool or a graphing calculator. So the first step to drawing or to determining the key characteristic of any rational function is, of course, to obtain the vertical asymptote. So the vertical asymptote is obtained first by looking at the denominator of the function. So we already know that since denominator cannot equals to 0, means x cannot equal to negative 5 over 2 in this case. And this would mean that this point will never exist, and we call this the vertical asymptote. That's first step. Let's look at the second step. Now, because this is a function of a real number in its numerator. So let me repeat that again. This being a function whereby the numerator is a real value, a real number, which means no matter how you do a division to it, it will never ever equals to 0. So in this case, it tends towards a very small number if the denominator is very, very large. Is large, or in another way of expressing, x tends towards positive, negative infinity. It will never ever give you a y equals to 0, and we call this the horizontal asymptote. So let's recall, we mentioned that it's important to find two asymptotes, which we already did. Now we need to find a point. So it's easy to find a point. You can just choose any convenient x values and substitute it in. And so in this case, we are able to obtain one point on the graph. So let's go ahead and sketch the graph. And if we remember, the two asymptotes are such, there is one asymptote along the x-axis, which we call y equals to 0. So these are our two asymptotes, and if we already know one point, we will know how the graph tends towards, and you can do a very quick sketch of this rational function f. We can pause this segment now and try to sketch this graph of y by yourself with the steps that were shown before you check the answers with us. So if we are to produce the sketch of this rational function, first of all, we want to look at the denominator. So we will know that x cannot equals to root 3 because that would make denominator 0. So let's put it down very quickly, and this would be our vertical asymptote. Secondly, we want to find the next asymptote. Now remembering that the numerator being a real value, so 5 divided by any number at all, there's no way you could actually get a 0. So which means the entire fraction over here, 5 divided by something known, y can never equals to 0. It can never equals to 0. We call this an asymptote, and in this case, y equals to 0 happens to be what we call a horizontal asymptote. So we have gotten two asymptotes. The third step is to find any known coordinate. So in this case, if we let x equals to 0, we are very quickly and very easily able to find the y coordinate, which is given by 5 over root 3. So here it's plotted, and because we already know that there are two asymptotes in this case with a known point, we do know then the rational graph will tend towards, and it will appear diagonally across as well. So this is how we produce the graph of this rational function.